So you guys will follow along with me.
Is this the hand thing?
Yes, exactly. This is the hand thing.
I love that hand.
So magnetic fields. So now we're talking about magnetic fields. And obviously, as you guys probably remember, magnetic fields have north poles and south poles and all that stuff. And so you guys remember that like poles do what? Do they attract or do they repel?
Repel.
Okay, so they repel. So go ahead and fill these in. Unlike do what?
They attract.
Yes, they attract. And there's no such thing as a magnetic monopole. In other words, as far as we know so far, there's no such thing as isolating a north or a south pole. Stanford thought they did. Stanford always tries to one-up Berkeley because Berkeley has all the really big discoveries, right? There's berkelium, for Pete's sake. There's californium, right? So Berkeley has two elements named after it, and there's no Stanfordium. So, Berkeley tries to trump Stanford, and Stanford tries to come out with it. They've got the linear accelerator, at least. Right?
I want an element.
Yes, the Middletonian, right? Talks a lot. He's got a lot of energy. Doesn't really get very inert, though. Doesn't really. No, it would be not inert, right? It would be highly reactive.
What are you saying?
Okay. So the direction of the magnetic field at any point in space is a direction indicated by the north pole of a small compass needle placed at that point. Okay, so basically it's whatever direction a compass needle points in is the direction of the magnetic field. So just like with electric field lines, right, the magnetic field at any point is direction. Yeah, perpendicular. No, wait. We want to say, sorry, is tangent. Right, the magnetic field at any point is tangent to the magnetic field lines. The strength of the magnetic field is proportional to the number of lines per unit area. So the more lines, the stronger the magnetic field, right? A positive test charge, positive Q, experiences a magnetic force from a magnetic field when the charge is moving. The velocity of the moving charge has a component perpendicular to the direction of the magnetic field. So let me pause to sort of explain that. Okay, so right-hand rule number 1 goes like this. The finger points in the direction of the magnetic field. So this would be the magnetic field. The thumb points along the direction of the, I should say, moving charge, right? Thumb points along the velocity. Okay, the velocity of the charge. The palm points in the direction of the magnetic force. And the equation is based off of that. So let me pause that to show how this works. Example says, let's go over what these stand for. So first of all, F stands for the magnetic force. Q is a positive test charge, just in coulombs. The velocity is in meters per second. That's how fast it's going. B is a magnetic field. Its units are in Tesla. And theta is the angle between the velocity of the charge and the magnetic field. Okay? So this first problem says a proton in a particle accelerator has a speed of 5 times 10 to the 6 meters per second. The proton encounters a magnetic field whose magnitude is 0.40 Tesla, and whose direction makes an angle of 30 degrees with respect to the proton's velocity. Find the magnitude and direction of the magnetic force on the proton. So we have to basically plug into our equation F is equal to QVB sine theta. QVB sine theta. Okay, so here's another equation we have to add to our memo quiz. So the force Now we're looking for its, so it's a proton, so what's the charge on a proton? Good, you guys should have that memorized by now. It's not mandatory, but you probably should. 1.6 times 10 to the minus 19 coulombs. The velocity of it, the object, 5 times 10 to the 6 meters per second. The strength of the magnetic field, 0.40 Tesla. And the angle it's making is 30, so we're going to plug in the sine of 30. Okay. My answer comes out to be really small because we're talking about a force on a really small object. On the proton, 1.60 times 10 to the minus 13th. What are the units for force? Newtons. Okay. Then it asks find the acceleration on the proton. How do I go about finding the acceleration on the proton? Yeah, take the force divided by the mass. So we get 1.60 times 10 to the minus 13 newtons divided by the mass of a proton. Where do we go about finding that? Okay, on our table of information, 10 to the minus 27 kilograms. So remember, that value is on your table of information. That's an electron. So 9.6 times 10 to the 13th meters per second squared. It's a really high acceleration. Okay? All right. So there's a really simple example of how to solve the force equation. So in Physics 1, we talked about the force, but we didn't have an equation for it. Okay? The difference now is we've got an equation. Okay. So this example here is an example of what happens to a positive charge in an electric field and a magnetic field. So it says the electric force F that acts on a positive charge in this particular example is parallel to the electric field. All right, so here we want to put in parallel to the electric field E and causes the particle's trajectory to bend in a horizontal plane. On the printout, does that come out okay? Does the picture come out okay? Can you tell it's horizontal? Okay. For object B, now this is a positive charge in a magnetic field. Okay. The magnetic force is perpendicular, okay, to both the magnetic field and the velocity. So this is perpendicular. Perpendicular. Now you don't have to memorize this. You just have to know that this is what would happen from the right-hand rule. Okay, and causes the particle's trajectory to bend in the vertical plane. Yes.
Why these two setups look like they're the same thing?
The one on the left, this is an electrical field. Okay, and on the right, that's a magnetic field. Okay, so that comes up. That is a really important topic. Multiple choice topic on the AP test. Being able to tell which way the charge goes in an electric field and a magnetic field. Okay? So just to make sure, let's just label this. This is the electric field, and this is the magnetic field. All right? The direction convention. So you should know there's some conventions for directions. So for coming out of the page, okay, we use dots. Okay, so just dots. This means that field is coming out of the page. Okay, and what I tell people to think of is the tip of arrows. So tips of arrows coming out of the page. And we use crosses or X's. Crosses. I put an X in for my S. Okay, so this means it's going into the page, which should be X's, right? And what I tell people to think of is the, well, what's the back of the arrow called? There's a
Feathers.
the feathers, but there's actually a term for that part. What is it
I
called?
think it's called the fletch.
Probably, I'm not
the fletching.
100% sure
Really?
on this, but I think it might be called a fletch.
Is that what it is? Okay. If that's what you guys tell me. Is that what did I spell that right?
Yes.
Okay. I've not heard of that before. Okay, so let me show you guys an example of this. Let me pause this. Okay, so we'll look specifically, I'm glad you asked about the magnetic field going in a circle, okay? So a really important topic here. The magnetic force cannot, so make sure you put cannot, do work and change the kinetic energy of the charged particle when it's going in a circle. Okay? The magnetic force always acts in a direction perpendicular to the motion of the charge. Hence, the displacement of the moving charge never has a component in the direction of the magnetic force. Okay? So there is no work being done. Okay, so the whole idea here, yeah, go ahead.
Will they ever give you like they'll tell you which way the force is going and which way the charge goes after, and then like ask you what the velocity is or
Yes,
something like that?
yeah, they could
So
do
it'll
either one.
always just be like the
The magnetic field and the velocity, yeah. Yeah. Exactly.
But won't you always be pointing like at the paper or away though? You won't be pointing like down or up?
Yes, yes. There's only been one case where they had a spiraled one, and it was pretty easy. And we'll go over that one. Okay. All right. Okay, so remember how we talked about all of our different types of centripetal forces, right? A satellite is experiencing what type of centripetal force? Gravity, right? An object spun around with a string is experiencing tension, right? If you're in the gravitron ride, that's the normal force keeping you inward. Remember the gravitron ride? What about if you're running or driving in a circle? Friction, remember, it's specifically static friction. Okay? Now, we're introducing, because we're talking about an object going around in a circle, in a magnetic field, we're introducing a new centripetal force, and it's the magnetic force. So this object going around in a circle is experiencing a centripetal force that's equivalent to the magnetic force. So when you have these kinds of problems, this derivation you need to be able to do from the original equations. Okay? So we in this situation, the centripetal force is equal to the magnetic force. Okay, so that should be a B. The magnetic force, right? The centripetal force, remember, is what equation? Okay, that's right, mv squared over r. And the magnetic force, we just finished saying, is qvb sine theta, but we'll just take out the sine theta part of it, because we'll assume that it's going perpendicular to the magnetic field. If I take this equation and solve it for r, okay, well, let's just, if we solve this equation for r, it simply becomes r is equal to mv over qb. So you need to be able to start from this equation. It cancels. One of them cancels, yeah. So you always start from this when you'll have one of these questions probably on your test or a quiz. always start from this equation first and show how you get from there to there, and then from there to there to get full credit. Okay? Don't just start off with this equation, because if you start off with that equation, you won't get full credit. All right? Okay. So this is the equation you would use for for objects going around in a circle in a magnetic field. All right? We're not going to do an example of that. I just gave you the equation for it. Okay? And how to set it up. Now, this next question is a question that does come up on AP tests pretty often. Okay? It says, and it refers to this picture on the right. It says a proton is released from rest at point A, which is located next to the positive plate of a parallel plate capacitor. The proton accelerates towards a negative plate through a small hole. The electric potential of the positive plate is 2100 volts greater than that of the negative plate. So the difference is just 2100 volts. Once outside the capacitor, the proton travels at a constant velocity until it enters a region of constant magnetic field of magnitude 0.10 Tesla. The velocity is perpendicular to the magnetic field, which is directed out of the page. Okay? So the first part is we have to figure out how fast it's going, how fast it gets when it gets from here to here. So what kind of problem is that? What kind of problem is that?
Kinematics.
No.
The vector.
It's actually an energy problem.
Energy.
Okay. So the first part is the energy problem. Okay. So we start off, if we draw out our little LOL thing, right? We got basically our charge. Okay. And we probably should also include the electric field in there. So inside here, we should probably include the electric field. Okay. Now, all of our energy at the beginning, when it's held up against the positive plate, all of that energy is what kind of energy? Yes, electrical potential, U sub E or EPE. And at the end, when it comes out of the other plate, what kind of energy do we have? Yeah, it's all kinetic. So we have essentially for our energy model, we know that the electric potential is equal to the kinetic energy. The electrical potential energy equation is what? Remember, it's just the QV, right? QV, when you're in a potential difference, the kinetic energy equation is 1/2 mv squared. Okay, let's not get these two v's mixed up. This is potential, and that is velocity. Okay, so we would end up solving this for v, velocity. So we'll solve it for the velocity first. Okay, and we would get the square root 2q, and the big V is the potential, over m. Okay, so we would plug into our equation. You know what? I'm going to move this up here to save some space. So we get V is equal to the square root of 2 times the charge on the proton. What's the charge on the proton? Good. 1.6 times 10 to the minus 19 coulombs. What is the potential? Okay, 2100 volts. And I'm going to divide that by the mass of a proton. Good. Negative 27 kilograms. And that gives me a velocity. That gives me a velocity, now I have this already, 6.3 times 10 to the 5th meters per second. Okay, so that's how fast it's moving now when it gets right there. Okay, that's it. This is the velocity. The question though is, what is the radius? Okay, we want to find we want to find the radius that it has when it goes around in the circle. So it's going to go around in the circle, Okay, we want to find this radius r. Okay, now we just finished saying that we would use this equation here. So let me get a different color here. So we're going to use this equation here. But again, when you're doing this on your quiz or your test, you want to start with this equation first. Okay, but because we've already done that, we can just plug into our radius equation, the mass, right, which is 1.67 times 10 to the minus 27 kilograms. The velocity, which is how much? It's right there. Good. 6.3 times 10 to the 5th meters per second. Okay. And we're going to divide that by the charge of a proton. 1.6 times 10 to the minus 19 coulombs. Minus 19 coulombs. Divided by the strength of the magnetic field, which is given to us right there, 0.10 Tesla. Okay, and that gives me an answer of 6.6 times 10 minus 2 meters. I should say meters. Okay, and so that's how we would solve that kind of problem. That's a problem that comes up a lot on the AP test because they're actually testing you on a bunch of different things with just one question. Okay, let's just going over all the different topics. Think of all the different topics they're testing you on just that one question. They're testing you on magnetic fields. They're testing you on electric fields, and they're testing you on energy. What else are they testing you on? Centripetal force. They're testing you on forces. So they're covering just about every topic in physics. With the exception of thermodynamics, heat and waves, and modern physics. But there's a lot in just that one problem. Okay? All right. So, again, what I...